Here we have an example of like a visual pattern. I have four different figures and I can see that like the quantity of squares is getting larger and I need to find a pattern in how it's growing. And also I need to see if I can find a formula, like an equation to calculate how many boxes there would be if somebody just said a figure number. Like how many boxes would there be in figure 57? And I don't want to count like every single one or draw every single one out all the way up to 57. That would be absurd. So we need to see if we can find a formula where just by knowing the figure number, we would know how many boxes there are. And in order to do that, we always make a table. So table is always going to have one really small column at the beginning for the figure number, which we always call n. Of course, you can call it any variable you want, but for whatever reason, the world has chosen n, and that's what we go with. So here we would have like figure 1, 2, 3, 4. You don't have to leave so much space. I don't know. I'm just always worried that it'll be too squishy. And then on the right-hand side of that line, it's actually not clear how many columns we will need. It will depend on how the working out goes, how many I need. If I find out that I'm doing like several calculation steps, I'll break this into several columns so that I can focus on what's happening in each calculation step. Okay, but I want to count systematically. And so it would be better if looking at the figure, I can focus in on squares or rectangles, like groups of squares that form a square or groups of rectangles, which sounds a little bit silly, but here's what I mean. So instead of looking at it like it is now, I would look at it like this. So I can see like I always have this bottom stack that's blue, and then appears this pink one, which is also growing as I go to the right and like increase in figure numbers. And then there's this orange one that appears, and then a green one appears, and presumably if I were to draw the next figure, like another one would appear on top. I won't be drawing that because it would take me 1,000 years. But we want to sort of like highlight or focus on these, and we want the groups of them to make rectangles because it's easy to calculate how many's in there. Like this one I'm pointing at, it's 5 wide and 4 tall, so that's for sure 20, because like 5 by 4 is 20. It makes it easier to count and it's easy to find a system. So as much as we can, you want to group together these boxes, or if they're like, sometimes they're stars or dots or whatever icon, group them together in squares or rectangles if possible. Okay, and now here I'm always going to write out the formula for calculating it using this like rows and columns or like heights and base for each of these color sections. So for example, in the first figure, we just have one block. That's not that useful. Sometimes the first figure, it actually is like a little bit too small to get anything meaningful from it, but okay, fine, we write it down. Then we go to the next figure, and there are 2 rows and 3 columns, because here it's like 2 by 3. So I'm going to write 2 times 3. That's supposed to be a tiny x. It's just so that we don't get confused between decimals and also with variables. Plus, now I have this pink section, and it has 2 rows and 1 column. And that's it. That's all I have. And I'll go ahead and say that that equals 8, although what I really am focusing on is like this expression, this formula that I'm using, because that's where I'm going to be able to find my general rule. And it's also how we'll justify the general rule. So like this, writing out what's multiplied and what's added together is very important. Okay, now look at figure 3. So we have 3 rows and 5 columns. I'm going to erase these, they're a bit annoying. So we have 3 times 5, plus we have the pink section, which now has 3 rows and 3 columns, plus now we have this orange section, which has 3 rows and 1 column. Okay, so I'll just use my calculator to add these together, and we will get 27. Again, I like to have 27. It's good. I want to see the total, but it's not really the thing that's going to help me solve what's the general rule, usually. If you're really, really good at seeing number patterns, then like maybe it occurs to you. But again, for the justification, we need this written out section. Okay, and then lastly, figure 4. So for the blue, we have 1, 2, 3, 4 columns, and 1, 2, 3, 4, 5, 6, 7. Sorry, 4 rows and 7 columns. And here I have 4 rows and 5 columns. Plus, now in the orange section, We have 4 rows and 3 columns. And then we need a green pen. And we have 4 rows and 1 column. Okay, so adding that up, we will get 64. So I'm going to slide the screen over because at this point, everything comes down to the table. The table is what's going to get us this pattern. And I don't actually think I'm going to add any more columns because I would have to like add more and more columns as I do the investigation because I realize it's adding more and more blocks like on top of every figure. Okay, so we look for patterns. We do want to see patterns like up and down. Like I can see the 3, 5, 7, so the next one's probably a 9. However, that will not help me find the general formula. That will help me find what's called a recursive formula, where like if I know the one before, I can find the next one. But I want a general formula where I could just know the figure number, like just know here goes 52 and just know like what I would have to fill out there. So using this idea, first let's look at 5. So just by looking at the number patterns, what do I think would happen? Well, I can see the first value is always the figure number, and then that is going up by 2, like it's odd numbers. So then that's going to be a 9. And now for the pink ones, again, the first one is the figure number, and those are also going up by 2. So like that will be a 7. And for the orange one, I can see the first number is again the figure number, also going up by 2. So for the green one, it will be, sorry, 5. I'm going to guess it would be 5 by 3, because let's just say that the pattern holds. We're adding 2 columns every time. But at this point, I would also be getting yet another new one. I've sort of run out of colors. We can go up to the top one with red. So even without drawing it, I can know that here is going to be a 5 times 1. So if I do this multiplication and adding, I will find that this is 125. I think I can see the patterns. But let's just see what happens if we jump forward. I want to jump forward enough spaces that I can't tell what it is just with the recursive pattern. Like I knew this was a 9 because this is a 7. But I want to go forward enough that like I wouldn't be able to know that. I'm not sure that I could at this point. Like I don't know how the 4 and the 7 and the 5 and the 9 are quite related. I can just see that the pattern's going upwards. So we need to find somewhere a pattern in these numbers in this equation. But I can see that they always have like the first value, it's highlighted here. This is always the same as the figure number. Like here it was the same as the figure number. So what happens if I factor that out? Let's look at just at this bottom one. So I'm going to put a 5 in the front of the brackets because each terms are the things like separated by the plus signs, have a 5. So then here I can see that this is 9 plus 7 plus 5. Let me use colors. Sorry. We have 9 plus 7 plus 5 plus 3 plus 1. Okay, that's a lot easier because now I can see definitely there's a pattern. It's that I have 5 numbers inside the brackets, same as the figure number, and they are like odd numbers from 1 to 9, or really like 9 to 1. So, okay, let's say now I jump forward to figure, let's just say figure 20. What would be this version of the formula if I were doing that? So it's going to have a 20 in front. I don't know what the end number will be, but I do know that it's going to be like a 1, 3, 5, until I get to the last number, and I know that inside here are 20 values. I'm going to slide this over. So the dot, dot, dot just means following the same pattern. My star looks really weird. Just going to do that again. Of course, I could put a variable there, but like I don't want to make this overly complicated. Okay, so I know there's 20 numbers, and I can see that this is an arithmetic sequence. If you can't see that, that means that this is not the unit you're doing in class, and that this is not the correct video to be watching. So like this is for when your class has already started or is already done with arithmetic sequences and series. So what I can see here is that this portion in the brackets is the sum of an arithmetic sequence. And we're familiar with that, and we know the formula. We know that there's a formula for the sum of an arithmetic sequence, and it is the figure, or like the number of terms in the sequence divided by 2, 2 times the first term, plus n minus 1 times the common difference. So we are going to use that formula because it's something that we're already doing in class. So looking just at this part, the 20 is hanging out in front. We'll deal with it in a second, but just the part in the brackets. So maybe I'm going to do this kind of symbol. I'm going to start like adding on the left. Sorry, adding on the right, because like I know this number. So the first term is 1. And the common difference is they're going up by 2. And I don't know what that last number is, but I do know that in total, there are 20 terms in this sequence because we knew that like the number of terms inside the bracket was the same as the figure number. For example, if we go to the second one, like there's 2 terms, second figure. Third figure has 3 terms. Fourth figure has 4 terms, and so on. So filling out our formula, we have S20 equals 20 over 2, 2 times 1, plus 20 minus 1 times the common difference. We could work this out step by step, but there's not really an advantage in doing that. I'm just going to put that whole thing in a calculator, but I don't have that already calculated in advance like I did on the other one, so this is going to take me a little bit longer. So 2 plus 400. So this total is 400. So coming back to our equation, let's go ahead and move this to the corner just that we have it for reference. So this is 20, and then in the brackets, that total was 400. So this turns out to be 8,000. Cool, great. I think I have it. I think I have an idea for how this goes. The problem is, in order to do this, this needs to be done with variables. So let me make this line longer. I'm gonna put row separators just to keep our focus. Oh no, I think I wrote crooked, so the line doesn't quite fit. Well, that'll have to do. Okay, so next row. Why are these lines like mega crooked? We'll survive. Okay, so I'm gonna put n. And how would the formula go again? So this is gonna be an n. I don't know what the last term is. It's also a star. It's not the same star, it's just a star. And I know it's adding together these odd numbers. And I know the total quantity of terms inside this bracket that I'm adding together are n, because it's the same as the figure number. So again, u1 is 1. The common difference is 2, because like I start at 1, and then this one is 2 bigger, and this one is 2 bigger, and the total number of terms is n. It seems a little bit weird to have like an n in 2 different places, but it's going to work fine for us. So again, referring to this formula over here, we're going to have Sn equals n over 2, 2 times 1, plus n minus 1 times 2. And in this time, we do have to simplify this. Like, I can't just know that number because there's a variable in the expression. And the whole point of these investigations is to find a formula that has an n in it. So we need to do like the algebra to make this go together. So 2 times 1 is 2. Expanding this bracket, so 2 times n and 2 times negative 1. Okay, continuing. So inside the bracket, 2 minus 2, that's nothing. So then I just have 2n. And we remember from multiplying algebraic expressions, like just recently, a couple weeks ago, these 2's will cancel. So this is n squared. So if I come back to where I was doing my equation, there was n, and now in the bracket is n squared. So I get n cubed. That's my general rule. This here is the rule. That's weird. Again. This is my general rule for calculating how many blocks there are in whatever figure number. So putting it together, I didn't give this a title. Maybe I will go with B for blocks. Sure. So the number of blocks in figure n will be n cubed. And of course, in the investigation, you need to verify this by plugging in specific values that I already know worked, like let n equal 4. Well, for example, okay, so like let's say let n equal 4. Then using my formula, this would be 4 cubed, which is 64. What did I get when I actually counted them all and put them together? 64. Great. So that's verified. Verify is plug a number into your formula and double check that it works for one of the ones that you already knew how many blocks there were. So this is a little bit short. Definitely more would need to be discussed in an actual paper. But the point of this is to have a system for how you could calculate something like this. And also my table definitely needs that same letters or variables that I was using. So what you can call this whatever you want to. Just call it something. I used B for block. So then in the final rule, you have that variable equals whatever your rule turned out to be.